All right. Hello, everyone, and welcome. My name is Maddie Hornsby. I'm the project manager for Riot. Welcome to Riot's Lunch and Learn series. This is the place where we highlight our speakers. Today we have with us Aparna, and she's with the Aurora Group, and she will be speaking on how no two white broadband technologies are the same. Just a couple of reminders as we are going through this presentation. This event will be recorded and uploaded to the Meetup channel where you all registered for the event. And if you have any questions, we ask that you just hold that till the end. With that being said, I'll pass it over to Aparna. Aparna, welcome.
Thank you, Maddie. Really appreciate it. And thank you all for attending in person and virtually. We have a few things to cover before we get going. We love our friends from the Riot for getting this all set up for us and actually announcing it and continue to announce it. So they're one of our favorite partners. Today, I will be highlighting Transphorm. But before we get going, I want to tell you all a little bit about the Aurora Group. We're a manufacturer's representation firm, and we represent all kinds of different electromechanical components. You'll get some highlighted here. We are engineers. We are technical people. We can support you. Just a little bit about what we do. We kind of provide a little bit of advice, support, guidance through technical challenges, and we help in the liaison for quotes, order samples, expediting, all those things you might need to get your product off the ground. Our company ranges through the East Coast. We mainly cover the Southeast and Florida. Here's a quick look at our team. We got Bob in South Carolina, Karen in Georgia. Kathy's our inside sales. I'm covering North Carolina together with Ken. And then we have Bruce covering Alabama, Mississippi, Tennessee. Here's our Florida team, Rick, Steve, Bob, and Ben covering various parts of Florida, also in support of electrical components and mechanical components. This gives you just a brief highlight of all the different types of mechanical components. No software, only electrical, hardware, and mechanical components touching all industries. Here's a quick look at the breadth of the current manufacturers that we support. And we're connected with all the organizations in our areas. And one of them, of course, is the Riot, who we love. Maddie and Caroline do an excellent job with the Riot and keeping us all connected in our community. We also work with all the distribution partners. So if there's a favorite, let me know. If there's a favorite is not on here, let me know. So right now I am done with my portion of it, and I am going to introduce both Tushar and Jenny from Transphorm. They're here all the way from California, and they're going to talk about GaN. And a few things to know about GaN. Highest efficiency, simplest to drive, enables lower system cost, and is manufactured in the US and Japan. Tushar is VP of Technical Sales and Field Applications, and Jenny is also the Technical Sales Manager in Field Applications. And now I'm going to turn the podium over to Jenny.
Hi, everyone.
So just give us a moment to switch computers.
Did you want to show yourself on the camera?
Oh, sure. Thank you.
Hi, everyone.
Thank you so much.
Jenny and Tushar.
Yeah.
All righty. Well, before I begin, I'd like to thank all of you who have arrived here. Thank you for your time. I'll go over some key concepts of Transphorm GaN. GaN has been in the industry for a couple of years already, and it's spiking throughout the semiconductor field.
Jenny, are you able to share your PowerPoint to the slideshow as well?
How do I do that?
Yep. So go back to, there's Zoom, and then you're just going to share your screen.
Security, share screen, right?
Share screen, yes, ma'am.
Okay. Got it?
Yes, ma'am.
Perfect. All right, so let me move this over. There you go. So GaN is the best in class for relevant voltage ranges. As you know already, you can't really get much more from silicon nowadays. So on this plot from power density versus the timeline, all the way to 2030, you're showing a performance plateau of silicon over here. BJTs, IGBTs, silicon superjunction, silicon carbide as well, and then now GaN. Our performance is still increasing. So in regards of GaN versus silicon and silicon carbide, there are key factors. GaN offers higher efficiencies, as what Aparna mentioned, with lower system costs and losses and power conversion. We can operate at higher switching frequencies as well. Cost-wise, we are beneficial because we offer lower system cost overall. Okay, so with gallium nitride, you can see better performance, higher power density, and lower system cost. The end markets for gallium nitride, as you can see here on the left side, power adapters, we focus on data centers, broad industrials, such as power supplies, and now we are in the automotive segment. This slide here highlights our product portfolio throughout the different types of power levels, 40 watts up to 10 kilowatts and above. As you can see here, we have different packages ranging from PQFN 8x8, 5x6, TO220s, TO247s, TO263. In the future, we will be releasing some modules. And with those modules, you can see performance, operational performance going up to the 100 kilowatt. Okay. We focus on, as I mentioned, wall plug adapters, servo motor drives, all the way to the driver train inverters. So we have leading solutions in adapters and chargers. This showcases what we are doing in regards to lower power operation, 45 watts up to 250 watts. Okay. Not only that, we are focused on the data centers as well. So we are now in a lot of different power supplies. The mega markets for GaN, as you can see, electric vehicles, 5G power devices, as well as the opportunity and a bit capability of working with 5G RF devices. So Transphorm GaN advantage in power systems. Our new technology, generation 4, it's now released. And as you can see, we have proven robustness and reliability. It is easy to drive our gate, our devices. We have a low voltage silicon MOSFET in series with our HEMT device. So that enables you to use many standard off-the-shelf drivers, ranging from 0 to 20 volts. No custom type of drivers is required. Our performance is much more better because we have a higher figure of merit. It's easy to design with our GaN. And we are quieter in switching. With that, you're able to assemble our devices much easier. So the Transphorm GaN advantage, we offer reliability, simplicity of drivability, designability, and reproducibility. As I mentioned, we offer higher efficiency. We have field reliability data with over 4 billion hours already. We're qualified for JDEC as well as AEC-Q 101 automotive. We have early life failure rates less than 0.3 fit, and we are in high production already. So Q&R and our portfolio, this is what we have available as of today. We have different types of products, different RDS-on devices ranging from 15 milliohms up to 480 milliohms, all rated for 650 volts. Over here, we have a list of AEC-Q1 qualified devices for automotive, okay? And they're qualified at 175 degrees C. We have released our 900 volt device as well, and more devices will be released soon. Transphorm and reliability. We have a higher breakdown voltage. Even though our devices are rated for 650 volts, they don't break down, as you can see here, until over 1500 volts. We have no dynamic RDS-on collapse, and we're able to switch up to 1000 volts. We are very transparent in what we do, so we provide all this information available on our website, transformusa.com. So as I mentioned, we are qualified in JDEC and AACQ 101 for automotive. We are the first and only qualified in that segment. I did mention that we are qualified at 175 degrees instead of 150. And I'll show you more information in the following slides.
And in fact, this performance and reliability is even better than silicon carbide. So I think that's noteworthy because a lot of the designs have been done with silicon carbide. So
of course, but we'll also discuss the advantage of gallium nitride against silicon, silicon carbide, and Emode GaN. So field reliability data, as I mentioned earlier, we focus on broad market adoption. So for Transphorm, we are already in adapters, data centers, gaming desktops, crypto mining, industrials, aerospace, and EV. This is the test performance test that we have done to qualify our automotive devices. High temperature reverse bias, HTRB, UHAST, temperature cycle up to 175, HTSL, HTGB. Not only that, but our threshold voltage for our devices is 4 volts. As you guys already know, there are better performance and opportunities for GaN versus silicon. We are 5 times more faster in turn on and turn off times than silicon, which means that we have much less switching losses and conduction losses. With that, we could have better performance and higher efficiency. Not only that, but we offer low QRR in reverse conduction mode, as you can see here, versus silicon. For silicon, the QRR is over 1,000 nanocoulombs at 9 amps, 400 volts. Whereas for our devices, you can see a QRR of 54 nanocoulombs at 400 volts, 9 amps. We do experiments throughout for all of our devices. And as you can see here, this is a boost buck converter half bridge. For silicon, operating at 100 kilohertz, you can see over here at this black curve, 100 kilohertz switching frequency. For silicon, the peak performance is at about 97%. Whereas for gallium nitride transform, we're able to switch at 100 kilohertz, 200 kilohertz, 300 kilohertz with higher performance. And this is a one-to-one comparison. Over here, this is a 3.3 kilowatt AC to DC power factor correction silicon comparison to gallium nitride, transform gallium nitride. What's this called? Our customer was able to do a comparison between interleave totem pole PFC and totem pole PFC with low frequency diodes. They saw the advantage. For an interleave PFC, they used about 22 total bomb counts and saw a performance peak of 98.5%. When they migrated over to using the Transphorm Bridges totem pole PFC solution, they were able to reduce the bomb count to 10. That reduced the total cost by 13.1% and increased performance to 99.10%. So that's an increase of about 0.6%. However, they wanted to see if they could reduce the cost even more. So they replaced the low frequency MOSFETs and used FRED diodes instead. That reduced the total cost to 7 components instead of 22, instead of 10. Reduced the total cost by 32%, but still maintained the high performance efficiency of 98.7. So it goes to show that with Transphorm Bridges totem pole PFC solution, you'll have better performance and lower system cost. So in regards to gallium nitride versus silicon carbide, there are very much a lot of advantages. Here's an analysis for that. Technical advantages can include improved performance, lower system cost. And I don't have to read through the lines of this because it's already seen. In regards to switching loss, Transphorm switches very, very fast. So we have a 50% reduction in crossover losses. For drain voltage versus time, GaN FET is much faster compared to silicon carbide. Okay, and this is a one-to-one comparison in the test in the lab. In regards to switching speed versus silicon carbide for Transphorm, dVdt, dIdt, we're much faster. In regards to energy losses, there's a 50% reduction in Transphorm in total energy losses over silicon carbide. As you can see here on the left side, Transphorm, we only have about a 474 microjoule loss or energy loss over current. Whereas for silicon carbide, it's about 953 microjoules at the same current level. So we always want to get the performance comparison real life in the lab. We've done this test before on a half-bridge synchronous boost buck converter using our GaN FET, 35 milliohm versus a 30 milliohm silicon carbide FET. We're able to push the performance to a higher peak of 99.2%. And we're able to operate up to close to 8 kilowatts. Okay, this is 240 volts in, 400 volts out, operating at 100 kilohertz switching frequency. Not only that, but we're able to increase the switching frequency to 70 kilohertz and 100 kilohertz. For silicon carbide, you can see the performance here on the left side that's only operating at 40 kilohertz. Transphorm's operating at 70 kilohertz, and we're able to have a higher performance throughout. This is up to 12 kilowatt. By increasing the switching frequency to 100 kilohertz for gallium nitride, we're able to still maintain the high performance at low power. Higher power, it's slightly lower, but then again, silicon carbide is only operating up to 70 kilohertz. So here are some waveforms, switching waveforms of VD versus time of GaN FETs, but this is for our generation 5 15 milliohm device versus the silicon carbide cascode FET. We are switching much faster. At the same time, our energy loss is much less compared to the newer silicon carbide cascode FET. 1150 microjoules compared to 2850 microjoules. In regards to temperature, Transphorm operates with lower power losses and operating temperature. So with our newer device, generation 5 15 milliohm, in a half-bridge synchronous boost buck converter, 240 volts in, 400 volts out, operating at 70 kilohertz. We're able to hit 12 kilowatts and maintain a total temperature of 101 degrees C. Whereas for silicon carbide MOSFET, they're only able to operate up to 11 kilowatts, and their device temperature is already, junction temperature is already 129.4. For silicon carbide MOSFET, 9.2 kilowatts, they could only hit, but their device temperature is already at 164 degrees C. Same goes for here, reduction of 17% to 37% power loss across both silicon carbide devices. This is where all the losses come from: passives, power loss, and switching. Okay. We did another study, half-bridge synchronous boost converter, with our 15 milliohm device versus the newest silicon carbide 18 milliohm device. With silicon carbide, they're limited in junction temperature. They're able to only hit about less than 10 kilowatts, about 9 kilowatts, 9.2. For transform, we're able to go up to 12 kilowatts with higher performance throughout. So here's just a summary of switching device material of gallium nitride compared to silicon and silicon carbide. So GaN offers higher efficiencies and enables higher efficiency on totem pole, PFC, and bridge topologies. We offer lower system cost, and we're not susceptible to single event burnout. Silicon carbide as well. For transform GaN versus silicon carbide, we offer higher performance, higher efficiencies, lower system cost, and we're not susceptible to single event burnout. So now moving forward, transform GaN versus Emode GaN. And I bet a lot of people already know about Emode GaN.
Can I present this Emode?
Oh yeah, sure,
Okay.
sure.
Okay. So I think Jenny talked about how our devices outperform, silicon as well as silicon carbide. So I did a presentation for the Power Americas in November, where we showed how GaN outperforms silicon and silicon carbide in the power range and the voltage range that we play in. So nobody in GaN or in Transphorm claims that GaN can beat silicon carbide at 1200 volts or 1700 volts. But in the voltage class that we are playing in, that's a 650 volt, 900 volt, some of the products, GaN clearly outperforms both silicon superjunction IGBTs, silicon carbide. But then it begs the question as to what is different about Transphorm GaN versus Emode GaN. There are two types of GaN. One which is called as the depletion mode, normally off, cascode GaN, which is what Transphorm does. And then there is an Emode GaN. And in the world, there are three companies actually who have their own GaN process. I mean, there are a few more, but the three main companies, that's Transphorm is one, TSMC is the other. The TSMC process is used by companies like Navitas or GaN Systems or ST Micro. And then the third one is Infineon. Infineon GaN is probably about 2 to 3 years behind TSMC as well as Transphorm. So I think the two main players in the market are TSMC GaN and Transphorm GaN. So that begs the question as to why Transphorm GaN versus Emode GaN. And there are a few things that I would like to share about how we differentiate against the Emode. First thing is the structure of the GaN itself is different. The Emode has a structure which is called as a P-GaN enhancement mode FET, and that structure is a Schottky barrier structure, whereas we have what is called as a MISFET, which is a metal insulator semiconductor, which is like similar to a MOSFET. Instead of oxide, we have insulator. So the GaN is a lot more robust and has a lot less losses when used both at high power and low power. And so we just tabulated a lot of the factors, about why the Emode GaN, how the Transphorm GaN differs and is a huge improvement over the Emode GaN, both in terms of the power level, ease of use, cost, efficiency, light load, standby power operation, the number of packages, BOM cost, the BOM count, as well as reliability. And we are clearly now winning in a lot of accounts ranging from, as Jenny mentioned, all the way from adapters to EV and everything in between. So from that point of view, the Transphorm GaN is extremely robust, has a huge safety margin. Our die size is smaller, So when the die size is smaller, the figure of merit is better compared to the Emode GaN. Our gate noise immunity is higher, and our thermal performance is better. In addition to that, the complexity of using the Emode GaN is, needs a lot of components that are not needed for driving the depletion mode GaN. Here you need things like level shifters that make it more expensive, not only expensive, but also lowers the reliability. So in terms of driving, so if you are using silicon or silicon carbide or IGBTs in your design, it's very easy to replace our GaN. In fact, the drive is exactly like silicon. It's not like IGBTs or silicon carbide need a negative drive, whereas GaN, our GaN does not need any negative drive. So you can drive it with standard silicon gate drivers. And then because we offer several different packages, we can, again, this was done by, I think this particular comparison was done with a SMD package, but we have different packages like TO247, TO263, that's the surface mount, as well as the TO220 for enhanced power dissipation. Oops. Another interesting factor is because of the structure, the leakage currents are much lower compared to Emode GaN. And of course, because of all these factors, we can see that, if we operate around a similar frequency and power level, we can get to almost 2.5 times or about 2 times the power that you can get with a Emode GaN. Today in the market, I don't think Emode GaN is shipping anywhere about 250 watts, whereas Transphorm is shipping all the way from 45 watts to, from all the systems that we are shipped today, it's about 250 watts, 45 watts to about 6 kilowatts. But then there are some designs that are done for traction inverters, which are like 30 kilowatt traction inverters. So these are for like small cars, The other interesting thing about our GaN, and again, it does not apply only to adapters. This slide was made for an adapter customer, is there are 3 types of GaN. One is Navitas calls themselves as the GaN IC. It's actually more like a driver MOS than a GaN IC. It doesn't have any controller, so then there is a discrete mode, and then there is the transform GaN, and we call it 2-switch normally off. So for driving, our GaN is, you don't need separate gate drivers. Usually controllers for low power already include gate drivers, and we can easily drive our GaN with the same gate drivers. Whereas if you have a enhancement mode GaN, you need things like level shifters, or if you have a GaN IC, it has a redundant gate driver in there. So compared to some of the leading GaN companies like TSMC, we can get much better efficiency even with a higher RDS on device. So it is counterintuitive. You have a higher RDS on device, but you still get higher efficiency at peak load as well as at lighter loads. And that's a very interesting thing. That's why we have been winning. So we started, Transphorm as a company started more in high power, in server power, in telecom power, in photovoltaics, inverters, whereas the other eGaN companies started more on the lower end in adapters and stuff. So of course we have been winning a lot of designs in the high power, high end devices, but we are also now substantially winning in the lower power, lower end devices. So skip this slide. So we also offer pin compatible devices with other GaN companies. In this case, so the previous comparison was with Navitas, which has the GaN, which they call as the GaN IC. And this comparison is with GaN systems. So these are the two leading competitors that we have. And this particular one, we have a pin compatible part with GaN systems. So we did some comparison. Actually, we did not do this. One of the customer did a comparison of our GaN versus the TSMC GaN from GaN systems. And you can see here clearly that we offer higher efficiency both at peak power as well as a lower power. And standby power is much better because the leakage current is much better. So this is the actual data that we have done. So in addition to the reliability and the 40 billion hours of data that we have, we also have a lot of competitive benchmarking versus our competitors, all in all the areas: silicon, silicon carbide, and other GaN, which are our three main buckets of competitors. We do offer several applications, examples on our website. We have eval boards. There are several eval boards all the way from 45 watts going to up to 4 kilowatts, various topologies: QRF, ACF, bridge topologies, totem pole PFC, and we also have some inverters. So overall, I believe that as GaN is now growing. There's a lot of interest in GaN. At APEC, I would say that of the all the power semiconductor makers, I did not see any booth for silicon carbide, I think, except Infineon. There are 8 GaN companies over there. I think silicon carbide is, of course, has been around. I mean, they started work in the 90s. And I think by 2015, 2016, silicon carbide had become mature. GaN work started towards the later half of 2000, 2008, 2010, and now it is maturing. And now GaN is also moving into the higher voltage range of 900 volts, 1200 volts. So I believe that the next 5, 10, 15 years will be the battle between GaN and silicon carbide. I think silicon is a previous year's technology. I think the battle is between GaN and silicon carbide. And so we try our best to outperform not only silicon carbide but also other GaN. And we hope we can work with you. If you have any designs, please talk to Aurora Group. I think they have several sales professionals in this area. So we work exclusively with them on the East Coast, in the Dixie States, in the Southeast. And, we will be happy to help you. Jenny is in Texas. We have design resources, not only here, but also in Asia. So if your design is done here, but your manufacturing is done in Asia, or if you want to specify something, do talk to us about your systems, and we'll be happy to help you. Anything from 45 watts to today we are doing up to 10 kilowatts, but we have done designs up to 30 kilowatts. So we'll be happy to help you. I think there's a lot of data here, but I think just to summarize, Transphorm GaN has definitely done well. We are a public company, by the way. The ticker symbol is TGAN. We're listed on NASDAQ. We are a small cap, about $400, $500 million market cap, but growing very rapidly. Both the market is growing. We can't keep up with the shipments, which is a good problem to have. We have very high performance, easy to design, both from a actual design point of view, but also from a system design point of view, with enhanced EMI capability. And when you say simplified assembly process, we have the right packages, that the power supply designers want, assembly packages, leaded packages, just TU220, TU47, both from a usability point of view, as well as from a power dissipation point of view. So again, we are here to, help you see how we can work together and hopefully, earn your business, along with Aurora. So,
Thanks, Tushar.
thank you.
Quick question. So
Yeah.
with the demand growing, what are your plans on adding capacity?
So
What is your current capacity now?
So as we stand today, our company's revenue is about 20 to 25 million. And again, we are a public company, so I cannot say more than what is already announced or what we have told publicly. We already said that we have more demand than what we can ship today, and so we are adding capacity. We are adding capex to both fabs here in Santa Barbara. So we have a big facility in Santa Barbara where we do design, we do prototyping, but also do part of the manufacturing. And we are also expanding the capacity in Japan. We have our own packaging houses as well, package and test that's done in Philippines. So we should be able to, I think, double to triple our capacity by end of this year, which is the plan, because if not, we won't be able to scale our company. So again, I don't know exactly how much the company will grow the next year. So this year has been last year and this year has been an anomaly. The company has grown 8 quarters in a row. We hope to continue for it to grow, the next, 8 quarters at least, based on the demand that we see. So yeah, I think it's a good story. I think we, especially in the power range and the voltage range that we play in, I think today GaN is untouchable unless a customer says, I just don't want to change my design because I'm lazy or, I don't want to be competitive. But I can tell you one thing, and there's nothing against any, country or company or anything, but China has gone to almost 100% adoption with GaN on low power. And this is very interesting, is that almost every adapter that is made, the notebook adapters, the cell phone adapters, they're 100% of the new designs are GaN. There is also a huge percentage of the server power supplies, crypto mining, gaming power supplies that are moving to GaN. And I see that less in US, Europe, as well as Taiwan and Japan. But China is, I think, about 5 years ahead of all the other countries combined in terms of adoption of GaN. I'm not saying what is right or wrong, but because of that, a lot of the early failures have also been vetted out, because somebody had to give GaN a lot of volume, for all the problems to be figured out. So I'm hoping, that other countries, companies, catch up on that, because end of the day, if you want to make your power supplies or power systems or your total systems more competitive in terms of efficiency, size, cost, just energy usage, consumption, it is important to go towards more power efficient material. So the two power efficient material, of course, are silicon carbide and GaN. And in the voltage class that GaN plays in, I think GaN will beat silicon carbide. In the voltage class that silicon carbide plays in, I think it clearly beats silicon and IGBTs.
Does anybody have any questions from the room here? Just feel free to ask. We have plenty of time for Q&A. I'm monitoring the chat box.
Yeah.
Do you think that the fact that China's moved this way and so the US and Europe hasn't, is that like a lack of knowledge or just systems already in place that they don't want to change? Why wouldn't they?
Yeah, so I think what has happened is China has its own ecosystem of end customers, end products. So if you look at the cell phone market, right, it's pretty, I think there are three main cell phone, ecosystems. One is Apple, one is Samsung, and all the others are in China. So Oppo, Vivo, and I'll tell you about multiple different segments. Okay, so it's just take the cell phone segment. So Samsung was very late in adopting GaN. Just started doing the designs, and I'm actually talking to them right now. Apple has been extremely reluctant, and Apple has been winning because Chinese companies are not selling their products in the US, not because they are not good. They're just not selling it in the US as much. But so Chinese products, Oppo, Vivo, Xiaomi, Lenovo, they went after fast charging. So you can charge the cell phone to about 80% within like half an hour. So it is not like we don't know how to use it. We are very risk averse. We are too worried about what if it fails. Whereas they looked at from, and also there is some cost differential, but how they looked at it is, hey, if we have 1 billion phones that are charging, and if I can cut a few watts, out of every, charge cycle, I think I can control the coal energy production. So this is how they have looked at it. And we have looked at it from a cost point of view, or why do I need to change something that is working? So it's the same as LED lighting, right? I mean, we still use in this country, I would say still about 60 to 70% is still incandescent and fluorescent.
Maybe 50%.
50%. I mean, you guys are experts, but if you go to China, it's like 99%. I mean, you can't find a fluorescent bulb at all, or you can't find a T8, fluorescent tube, or a regular bulb or a tube at all. Like everything is LED. Now, if you look at our bigger companies like HP or Dell, compared to Lenovo, both in servers, in telecom power supplies, everything has changed to GaN or silicon carbide over there. One of the anomaly here is Tesla. I think they went to silicon carbide a lot faster, but they were the only ones in the town initially. I think it's a matter of them also not wanting to invest more in silicon and IGBTs because like they didn't put any landlines, right, for a long time. They went straight to cell phone towers. So in here, instead of spending a lot of time and money on, older technologies, they went straight to the newer technologies. So the design capability of the engineers there is, I would say, definitely not as good as here or some of the ODMs of the US companies, but we are just so risk averse. If it is slightly more expensive, we'll say, no, purchasing will cut this, shoot this. But there, purchasing is given instruction to adopt new technology and still make it a commodity. So it's a mindset change, So everything there is smaller, faster. I mean, I shouldn't say this, but I'll ask a question, how many taxis in US are electric vehicles? Probably 0.1%, I went to Shenzhen in 2019 and, I was shocked, how many taxis, what percentage of taxis are electric? And anybody want to take a guess?
50%.
No, you're wrong.
90%.
100%.
Oh, God.
All the taxis are, and they are so much better than, no offense to Tesla, but so much better to ride in with all the electronics and the comforts. Not every car is a luxury car. So just the adoption of new technology there is so rampant. Some of the US ODMs, right? I was talking to Doug, like Artisan, or they're so slow, and they're winning because they have monopolies, or I won't say monopolies, but there is a barrier to entry for some of the things that are made. Not everything made in China is perfect, and not everything we make or our ODMs make is substandard. And I'm not saying that. What I'm saying is there can be a good intersection of both the new technology, making it cost effective and making it reliable. And we are just a little slower. 60% of our sales actually do come from China as well, of the product sales, because just the adoption is very high.
Do you have a technical question?
I have a different question.
Okay.
What is the sourcing of gallium nitride? Like, is it more readily available in silicon?
So yeah, so gallium nitride is, so first of all, the base is silicon. So we don't actually have a gallium nitride ingot. So sourcing of a gallium nitride ingot is almost impossible. There are a few companies who actually do what is called as GaN on GaN. We do what is called as GaN on silicon. So silicon is just silicon. So silicon is available, the sand. So you make the silicon ingot, and then we grow gallium nitride on it. So gallium nitride is grown by a process called as MOCVD, metal organic chemical vapor deposition. And that is just a matter of mixing the gases and growing the epi. So that is plenty available in plenty.
I think you have a slide that shows
The structure, right? Yeah. So the thing is, that is, there's no issue of gallium nitride. But gallium nitride ingots, so if you start with the material like gallium nitride on gallium nitride, that is not only difficult to make, but it's also very premature. So maybe 50 years from now, it should be, I won't say 50, but there's a company called NextGen, who does what is called as GaN on GaN. Probably they'll succeed after 10, 15 years, but today we are doing GaN on silicon. So there's no issue of the material. Similar to silicon carbide, right? Yeah.
Praneeth has a question.
Yeah, I had a question on the low voltage MOSFET. Does that picture show that?
This is the low voltage MOSFET, this is the low voltage MOSFET. This is the GaN.
Okay.
So we have a 2-chip normally off.
Mm-hmm.
So this is the low voltage MOSFET that's sitting on the GaN.
Oh, it's like a
It's like a stack die.
Okay.
So in this case, it's a stack die. In the case of the low power stuff, they are sitting side by side.
Mm-hmm.
So it's a multi-chip. And here you put this because that you want to reduce the lead inductances.
Can you make it bigger? You have to get it out of presentation.
We can make it bigger.
Just grab the photo and expand it, make it larger. You have a mouse?
This is the mouse?
Yeah.
There you go. Much better.
So this is the silicon. This is the GaN. So the silicon FET sits on the GaN FET. So we make a specific silicon FET. It's very interesting. So this is the gate of the silicon FET, because we drive the gate.
Mm-hmm.
This is the drain of the GaN, because that's connected to the high voltage. So this is a gate source drain configuration, and the source tab is the bottom. So this is a source. Now in this case, so there is a GaN here. I can use the board, right? There is a GaN. So the source of the GaN is connected to the drain of the low voltage MOSFET. This is the source. So the source, sorry, the drain of this device is actually on the bottom. So it's a vertical device. And this is the source of the GaN FET is below this. So just bond together. Yeah, it's a very interesting design. But on the lower power, they sit next to each other, and then there are bond wires. But those are really small. So these are much larger devices.
And what's the voltage of the low?
30 volt FET.
30 volt.
Because the threshold of the GaN device is around -20. So it needs just 5 volts higher, but there is some margin, So
You make that also, or
we
buy
actually we specify that, and then we buy it from other companies.
When you mentioned the Chinese market, it made me think of the environmental impact. And I'm wondering what you know about or what your company's looking into as far as recycling efforts, especially your product versus silicon. What's the future for that? You talk about 20 years from now, 50 years from now, but that's something that I think just ought to be part of when a company or a country is considering adopting, such an amazing new technology. Sometimes things are cheaper, better, but they might be really, more difficult to. But anyways,
They are not cheaper. Today, GaN is more expensive. Clearly more expensive than silicon, at least like for part to part, right? Let's say a 480 for low power, let's say 480 milliohm device, silicon is around 30 cents. GaN, I don't know broadly, and I'm not specifically, but it's between 60 and 75 cents. So it's about 2x higher. As the power level goes up, of course, it's not the gap goes down. But I think if you have a device that is better, you can also make things smaller. Power supplies, you can make power supply smaller. So it says environmental impact actually is positive on the using newer technologies. Like, you save so much on power generation. You save so much material used in these devices, used in the systems. So the environmental impact is actually much better of the newer technologies. In 2008, I remember, that Beijing, they had to shut down, cars on the road, and they had to shut down the coal plants. In 2022, in the last 10, 12 years, and this is something I saw on Netflix, okay, not my knowledge, but on Netflix, is that China planted more forest combined, more than the entire world combined. So they have made a lot of environmental progress as well, not only in the actual, planting, but also on adopting newer technologies. Like if 100% of the cars, taxis are, and they have a large population, right? The 100% of the taxis are electric. Two things are good. One, there's a more consumption of power electronics, but it's also a good impact for the environment. So companies like ours actually benefit, and the environment also benefits.
Those presentations be available.
Yeah. And we can share actually more. And today was more of a comparison of our technology versus others, and a very high level view. There's a lot of work that has gone into this over the last 10, 15 years. And we can also send another presentation that we did for Power Americas that talked about all the topologies that were used from low power to high power. You guys are experts on power topologies. So there's a lot of power topologies that we used
Yeah, everybody who registered will get the presentation and the video link.
Yeah.
So there's no more real technical questions that are sort of broad for everybody. We could kind of take some last minute ones and then close. Maddie?
That's great.
Yeah.
Do we have any questions online?
No. Doug asked the same question that somebody else asked. Hey, can we get these slides? And the answer is yes. So there's a lot of information to digest here. So,
Yeah,
good.
we had some, good meetings with a large power supply maker yesterday with Ken. And, that company is also, I should say they are also way behind, in the adoption. They're still just evaluating.
Yeah.
So it's interesting, that we hope we can, for example, your company, if you specify, right, to use this or investigate, we'll be happy to help your, but sometimes what happens is I've also seen that the ODMs or the power supply ODMs, they also, kind of influence the companies here saying, hey, this is what you should be using, because they haven't done some of the work, already. So
You guys have offices in Taiwan and Shenzhen and those.
yeah, so we have an office in Taiwan. We have an office and actually I manage all these offices. So Philippines, I don't manage the office, that's in operations. So Philippines has more assembly and test. Here we have so it's very interesting, our company started in Santa Barbara and we still have a factory in Santa Barbara that does the epi, because epi is what so on silicon we grow the gallium nitride, so that's the epi portion. So that is specified and done here, and that's the secret sauce, building the this thing. So our supply chain is very much in our control,
Yeah, it's a robust.
and not left to the vagaries of geopolitics, hopefully.
Well, thanks, Tushar.
Thank you.
You want to go ahead and close?
Thank you to everyone who joined us in person and online. I will send you all a message when the recording has processed, but we appreciate it and feel free to stick around for some other questions. But we look forward to seeing everyone else at future Lunch and Learn. So thank you very much.
Thanks, Maddie.
Thank you all.
Thank you.